I welcome you all to lecture number 32 of this course on knowledge-based systems in engineering. Now today I will be discussing a topic named scheduling genetic algorithm. Some of you might be knowing that optimization is a very difficult type of problem, and it is much more difficult compared to your ordinary optimization problem like gearbox, optimal design of gearbox, optimal design of spring, and so on. Now let us try to understand the difficulty of this type of optimization problem called scheduling optimization problem. Let me take one example. The example of this particular scheduling problem, there are many problems. For example, say how to determine the optimal schedule of your class routines for the institute and the department. It's a very difficult problem. I know the difficulty because I was professor in charge for the whole institute for 4 years of timetable. Okay. So I know the difficulty. It is extremely difficult problem. Okay. Another example could be very popular and all of you know. Supposing that there is one salesperson, like traveling salesperson, and that particular salesperson will have to visit a number of cities, say 10 cities, by touching each city only once and by covering the minimum distance. This is another very popular example of scheduling optimization problem. Okay. Now, in ordinary optimization problem, what we do is we try to find out only the distance between the two cities, like the distance between Delhi and Kolkata, say. Okay. So we try to find out the distance between Delhi and Kolkata. So we can find out very easily. Okay. And we can also find out what could be the minimum distance if I want to touch say 5 cities only once by following a particular the sequence. But in scheduling problem, we'll have to consider a more difficult situation because here we do not consider only the distance between Kolkata and Delhi, but we try to find out the relative position of Delhi with respect to Kolkata, whether Delhi is towards north or towards south or toward east or west with respect to Kolkata, that also we consider in scheduling optimization problem. But that is not the case with the ordinary optimization problem like gearbox optimization or spring design optimization or any other like shaft design optimization and so on. Okay. So I hope you have understood the difficulty of this particular the scheduling optimization problem. Okay. Now, ordinary genetic algorithm, which I've already discussed, you can use to solve the ordinary optimization problem. But if you have got a scheduling optimization problem, you cannot use the conventional genetic algorithm. Okay. The conventional crossover operator of the genetic algorithm is not going to help us. Okay. But it is very unfortunate as a researcher in this particular field for such a long time, I've seen a number of so-called good international journals papers have been published where scheduling problem has been tackled using the ordinary genetic algorithm. It is totally wrong. And let me allow to say that I have seen a few papers from our own institute, okay, where scheduling problem has been solved using the ordinary genetic algorithm, which is totally wrong. Okay. Now, the reason I have already told that scheduling optimization is a very difficult problem, and to tackle that, we need a special type of crossover operator. Okay. Now, before I proceed further, let me tell you that handling the scheduling optimization problem is much more difficult, and it is much more difficult for me to teach this particular topic, that too without the help of a chalk and duster on the board. Are you getting my point? So if I want to easily explain the principle of scheduling GA, I need chalk, duster and a board. And unfortunately, today I'll not be getting that also. So it has become a very difficult problem for me to teach you actually scheduling genetic algorithm, okay, easily. Are you getting my point? And that is why I'm just going to request you one thing. All of you, please sit with one notebook and one pen. Okay, I'll give you time. So please sit with one notebook and pen. All of you, please do that. Okay, because I cannot use board, and I'll be moving very slow so that I'll be giving instruction and you can follow on the notebook. Okay, and you'll be getting the solution. Okay, so I'll be moving very slow. Please maintain a notebook and sit with a pen. Okay, and let me proceed, but I'll be moving very slow. Okay, so I'm just going to discuss the scheduling problem, how to find out the optimal schedule. Okay, so scheduling problem is a special class of optimization problem in which not only the position of different elements, but also their order and adjacency are important. Okay, so we do not consider the distance between Kolkata and Chennai. Okay, but we'll have to find out whether Chennai is on north side or south side or east side or west side with respect to Kolkata. That is also very important. Are you getting my point? The moment I was just trying to find out the optimal schedule for the whole institute. It was a very difficult task, I should say. Okay, because I'll have to consider a number of functional constraints. For example, the same teacher should not be assigned two courses in the same slot. Okay, the same student should not be assigned two classes on the same slot. I'll have to follow the constraint related to the number of rooms available in our Nalanda complex. Okay, I'll have to consider the students attending class in the Nalanda complex, okay, should not move fast to the main building to attend another class. Okay, so similarly, there are many such functional constraints. And after satisfying all the functional constraints, getting the optimal schedule for your classes for the whole institute, it was an extremely difficult problem for me. Okay, so I still remember the difficult situation I had to face while determining the optimal or the near optimal class schedule for you people for the whole institute. Okay, because here order and adjacency are very much important. Let me concentrate on the TSP problem, traveling salesperson problem, the very famous problem. Okay, so the statement of the problem is such: a salesperson will have to visit, say, all 10 cities, and each city has to be visited only once. Okay, and the traveling salesperson should visit all the cities once by covering the minimum distance. How to determine that particular sequence? How to determine that optimal sequence? That is nothing but the scheduling or the scheduling optimization problem. Okay, now today I'll be discussing like how to solve using a special type of crossover operator in genetic algorithm. Now, before I go for that, let me tell you what is the problem with ordinary genetic algorithm which you have already studied, and the crossover operators like single point crossover, 2-point crossover, multi-point crossover, uniform crossover, and all such things. If you use this type of conventional crossover operators of genetic algorithm to solve the scheduling problem, there is a possibility that you'll be getting some optimal schedule which has got no practical meaning. Are you getting my point? And there is every possibility that you'll be getting some invalid schedule as the optimal schedule. Okay, to avoid that, actually we'll have to use a special type of crossover operator which I am going to discuss today. Okay. Now the scheduling problem, it could be either symmetric or it could be asymmetric. What do you mean by the symmetric scheduling problem? The distance between I and j is same is the distance between j and I. Okay, that means there are two ways, two roads available. One is from I to j, another is from say j to I, side by side, parallel. Okay, and if the distance between I and j is equal to the distance between j and I, that is called the symmetric scheduling problem. And if it is not equal, okay, that is called asymmetrical scheduling problem. Okay, sometimes the roads are available only in one direction between the two cities. Okay, the reverse direction road may not be available, might be you'll have to come through one intermediate city or the via city. Okay, and in that case, dij will not becomes equal to dji, and that will become asymmetrical scheduling problem. Okay. Now there are two types of TSP, traveling cells person problem. One is called the fully connected TSP, another is called partially connected TSP, and if it is partially connected, that has to be asymmetrical. Okay. Now let us try to understand what do you mean by the fully connected TSP. So by fully connected TSP, we mean that each city is connected to each other city, okay, in both the ways, in both the directions. Let me repeat. By a fully connected TSP, we mean that each city is connected to all the remaining cities in both the directions. That is called the fully connected TSP. Okay. And if it is not followed, okay, between any two cities, that is called the partially connected, and if it is partially connected, it has to be asymmetrical by definition. Okay. Now this is nothing but the example of a fully connected TSP. You can check any city is connected to the remaining cities in both the ways, directly connected. So this type of TSP is known as the fully connected TSP. Okay. Similarly, this is the example of the partially connected asymmetrical TSP. You can see that CT2 is connected to CT6 in one way, in one direction, but there is no direct connection from 6 to 2. So this is an example of partially connected asymmetrical TSP. Now I'm just going to tell you one fact. Please listen to me very carefully and you will understand the real difficulty of this type of problem. Okay. Now let me take a very simple example. All of you use your notebook and the pen. All of you, please use the notebook and your pen. I'm also going to use my notebook, okay, and a pen. So all of you, please use one notebook and pen. Okay. Now you write down on the notebook, supposing that there are three cities, say city 1, city 2 and city 3. All of you, please write down city 1, city 2, city 3. Now, there is a traveling salesperson, and this traveling salesperson will have to visit all three cities once by following some sequence. What could be the possible sequences? Now, one sequence could be, you write down on your notebook, one is 1, then 2, then 3. This is one sequence. The second sequence, 1, then 3, then comes your 2. Then the third sequence, let us start with 2, then you go to 1, then 3. Fourth sequence, let us start with 2, then comes your 3, then comes your 1. Then comes your the fifth sequence. Let us start with 3, then you go to 1, then you go to 2. And the sixth sequence, start with 3, then you go to 2, then you go to. So how many such sequences are possible? There are 6 sequences. So there is a maximum of 6 sequences. So if there are 3 cities, 1, 2 and 3, what is the maximum number of sequence possible? That is nothing but 3 factorial. All of you know. And 3 factorial is nothing but 3 multiplied by 2 multiplied by 1, that is equals to 6. I think I'm clear to all of you. Okay. So if the TSP involves n cities, so there will be a maximum possible sequences of n factorial. There could be n factorial possible sequences. Now supposing that there are 10 cities, small n is equal to 10. So how many such possible sequences? There will be 10 factorial. It is a very large number, 10 factorial. So if there are 10 cities, so GA will have to search for each of the 10 factorial sequences before it can find out the optimal sequence. Okay. So I hope you have understood the difficulty involved in this type of scheduling problem. Are you getting my point? So it is an extremely difficult problem. Okay. So I hope you have understood the difficulty. So if there are n cities, there are n factorial possible sequences, and GA through a large number of iterations will try to find out that particular optimal sequence which corresponds to the minimum distance traveled. Okay. So I hope I'm clear to all of you. Okay. And I hope you are able to understand the difficulty associated with this type of problem. Okay. Now here I have written simple genetic algorithm with conventional crossover operators may not be suitable for the scheduling problem. Okay. And that is why you'll have to use a special type of crossover operator if you want to handle the scheduling optimization problem. Okay. Now, if you see the literature, there are some special type of crossover operators available to tackle this type of problem using genetic algorithms. Okay. For example, say the first one which I should discuss, that is called the age recombination crossover operator to be used for the scheduling optimization problem. Okay. So let us try to understand the principle of age recombination crossover operator, which was proposed in the year 1991 by Whitley and others. Okay. So let us try to understand the principle of age recombination. Now, what is our M? GS should be able to find out some optimal sequence, but that particular optimal sequence has to be feasible. Otherwise, there is no meaning. Okay. Now, as usual in crossover, there are two parents which are going to participate and they will be creating two children solutions. Now, let me take a very simple example. One TSP problem involving, say, 9 cities. 9 cities means we have got 9 factorial possible combinations of the sequences. Okay, it's a very difficult problem. Now, supposing that parent 1 is such, which indicates the sequence of city 1, 2, then 3, 4, 5, 6, 7, 8, 9. Say this is parent 1. Okay. And parent 2 is 9, 3, 1, 4, 5, 8, 2, 6, 7. And remember, not even a single city is considered more than once. So one city will be considered only once. Okay. Now, if these two are the parents, how to find out the feasible children solution using the age recombination crossover operator? Now, here if I use the conventional crossover operator like single point, 2 point, multi-point and all such things, there is a possibility we'll be getting some infeasible solution. A large number of infeasible solutions we'll be getting. But as I told, unfortunately, this mistake has been done by many researchers working in this particular field, and consequently, a large number of erroneous papers have been published in so-called good international journals. Okay, but we never did that mistake. Okay, we never committed that particular. We have also published a large number of papers on this particular direction, but we have taken all the care. So we did not make any mistake in scheduling optimization. Okay. Now let us try to understand the working principle of age recombination. Okay. Now supposing that this particular problem is a partially connected asymmetrical TSP, which is more difficult to handle compared to your fully connected symmetrical TSP. Okay. Now, supposing that the connectivity table or the age table is something like this. Say CT1 is connected to CT2, it is connected to CT9, one is directly connected to CT3, and one is directly connected to CT4. But one is not directly connected to 8, or one is not directly connected to 5. If you want to connect 1 with 5, I'll have to take some intermediate CT or the via CT. Okay. Then comes your CT2 is connected to 1, 3, 8 and 6. 3 is connected to 2, 4, 9 and 1. 4 is connected to like 3, 5 and 1. 5 is connected to 4, 6 and 8. 6 is connected to 5, 7 and 2. 7 is connected to 6, 8 and 9. 8 is connected to 7, 9, 5, 2. And 9 is connected to 8, 1, 7, 3. So this shows the connectivity of the CT. Okay. Now, if it is a partially connected asymmetrical TSP, how to find out the feasible children solution corresponding to these two parents? Okay. Now, I'm going to discuss the principle of age recombination. It is very simple. Now, let me read it out. Then I'll be explaining once again. I'll be go back to the previous slide. Okay. Now, what is our aim? Our aim is to find out two children solutions from the two parents. That is child 1 and child 2. Now, let me read it out, the procedure. Let us start the child tour with the starting city of parent 1, that is your city 1. Okay. Now, let us go back to the previous slide. So we are going to start with the starting city of parent 1, that is a city 1. You can see that city 1. So we are going to determine child 1, and the starting city of child 1 will be the starting city of parent 1, that is your city 1. Are you getting my point? Now all of you, please do one thing. So this particular connectivity table, please write down on your notebook very soon. 1 is connected to 2934, 2 is connected to 1386. All of you, please write it down. I'm waiting. Please write down. So this particular, the connectivity table. So I hope you have already written this connectivity table, all of you. Okay. So let us start discussing. Now, the first city of child 1 that has been selected, and that is nothing but city 1. Okay. So you just start writing your child 1 like this. Okay. So you just write down child 1, the starting city is city 1. Up to this you write down. Okay. After that you listen to me. Okay. Okay. Please come back. Come back to the age table. Okay, let me start. Now, for child 1, the first city I have already selected, that is the city 1. And once you have selected city 1, you remove all the entries of city 1 from the right hand side of this age table. Please do it on your notebook. Let me repeat. Once you have selected city 1, please remove all the entries of city 1 from the right hand side of age table. So this one is removed, you cut it. This one is removed, you cut it. This one is removed, and this one is removed. So there are 4 entries of city 1 on the right hand side of age table. Okay, you simply cut them. Okay. Now you concentrate on, you come back here, city 1. City 1 is connected to city 2, city 9, city 3, and city 4. Now what I'll have to do, I'll have to check the connectivity of city 2, city 9, city 3, and city 4. Okay. Now to check the connectivity of city 2, let us come here. City 2 is connected to now 3, 8, and 6 because 1 has been removed. Okay. Now city 9 is connected to 8, 7, and 3 because 1 has been removed. Now city 3 is connected to 2, 4, and 9. 1 has been removed. And 4 has been connected to 3 and 5 because 1 has been removed. Now you concentrate on these 4 cities, their connectivity records. So out of these 4 cities, like 2, 9, 3, and 4, 2 is connected to 3 cities, 9 is connected to now 3 other cities, 3 is connected to 3 other cities, but 4 is connected to only 2 cities, 3 and 5. Are you getting my point? So out of these 4 cities, you select that particular city which is connected to the minimum number of cities. Okay, that is your city 4. Because 4 is connected to only 2 cities, that is 3 and 5. Okay. So on the child solution 1, after city 1, you please write down city 4. Are you getting my point? So in the second position of child 1, you write down city 4, the way I have written it here. You see, the way I have written it here. Okay. Now once again you go back to the age table. Okay. And once you have selected city 4, all the entries of city 4 you remove from the right hand side of the age table. So 4 has been selected, so 4 has to be removed. You cut 4 here, remove 4 here, and there is no other 4. Okay. Now you concentrate on the connectivity record once again of city 4. 4 is connected to 3 and 5, only 2 cities. See the connectivity of city 3 and the connectivity of city 5. Now 3 is connected to now only 2 cities, 2 and 9, and 5 is connected to 4, 4 is removed, 6 and 8. Okay, so both city 3 and city 5 is connected now with 2 other cities. Okay, so there is a tie. And if there is a tie, you can select any one out of city 3 and city 5. Select any one. For example, say I have selected here, I hope I have selected city 3. Okay, and once again, if you have selected city 3, so you'll have to remove all the entries of city 3 from here. Okay, on the right hand side of age table. And you follow that particular the procedure so that you can consider all the 9 cities. Okay, and if you follow that method, there is a possibility you'll be getting a child solution, that is child 1, and that will be a valid child, that is 1 4 3 2 6 5 8 7 9. Now this particular child 1, you'll have to check its feasibility. 1 4 3 2 6 5 8 7 9. Okay, let me check once again the connectivity record, whether this is a valid child or not. That you'll have to check it. Now from this particular figure I can check very easily. 1 is connected to 4, 1 is connected to 4, 4 is connected to 3, 4 is connected to 3, 3 is connected to 2, 3 is connected to 2, 2 is connected to 6, 2 is connected to 6, 6 is connected to 5, 6 is connected to 5, then 5 is connected to 8, 5 is connected to 8, 8 is connected to 7, 8 is connected to 7, 7 is connected to 9. So you see, this is a valid child solution. So using the principle of this age recombination, I have got a valid child solution from the parents. Okay. So this is correct and nobody can claim that this is a wrong one. Okay. So this is your child 1. Similarly, by following the similar procedure or the same procedure, okay, you can find out the child 2, where the starting city of child 2 will be the starting city of parent 2, that is 9, and follow the same sequence. You do one thing, You once again write down a phrase age table following the same connectivity, and whenever you find time, you try to find out child 2 and you note it down this child 2. I am sure you will be getting this valid child 2 also. Okay, and you can check its validity that this particular child 2 will be a valid child from your that connectivity figure or the connectivity graph. Okay, so I hope I'm clear regarding the working principle of age recombination. Am I clear to all of you? I hope I am clear. Okay. Now I'm just going to discuss another very popular crossover operator that is called the order crossover used for handling the scheduling problem. Okay. Please stop your audio. Please stop your audio.
Sir,
Now,
excuse me.
yes.
Sir, for the age recombination,
Hmm.
you have told that we can consider any one of the cities if there
Yes.
are same. Sir,
Yes.
after considering one of the cities, we have to check that whether that child is connected to following that order.
Hmm.
If that is
Now,
not,
in case of tie, in
yes,
case of tie, if there are two solutions, both are valid solutions. Are you getting my point? Because a particular city is connected to two other cities, and those two other cities are connected to equal number of cities. So in that case, there is a tie. Okay. Whenever there is a tie, both the solutions are feasible. Are you getting my point? That's why there is a
okay,
tie. Okay. So you need
okay,
not worry. Okay.
okay, sir, thank you.
Uh, So I hope it is clear to all of you now. Now let me start with this order crossover. This order crossover is very popular. Okay. Now this order crossover, it was proposed by Davis in the year 1985. Okay. Now let me try to explain the principle of this particular the order crossover. Now, to start with discussing the principle of order crossover, let me once again take two parents, parent 1 and parent 2. Parent 1 is like 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 cities. And parent 2 is 3, 4, 5, 1, 2, 9, 8, 7, 6. Okay. These two are the parents. They are going to participate in order crossover to find out two valid children. Okay, as I told, I'll be moving very slow because it is very unfortunate I cannot write anything on the board. It becomes very easy for me if I can write on the board. Okay, now as I'm unable to write on the board, I'm requesting you all to write these two parents on your notebook. Okay, parent 1 and parent 2. All of you, please write it down. Parent 1 and parent 2, please write it down. And once you've written this parent 1 and parent 2, you please draw these two crossover sites. So this is the first crossover site, the second crossover site, and crossover sites are also selected at random using the random number generator. Okay. Please write it down, then I'm going to explain. What is our aim? Our aim is to find out child 1 and child 2. Okay. And that particular two children solutions are to be valid. Now, what is the principle? Principle is very simple. I'm just reading it out. A part of one child solution is obtained by copying directly from a part of one parent and the other part of that particular child inherits the order of remaining elements of other parent. What does it mean? Our aim is to find out two child solution, that is child 1 and child 2. Now to get child 1, what I do is the cities lying between the two crossover sites on parent 2 are directly copied after keeping their positional information intact. What does it mean? To get child 1, what I am going to do is I am just going to directly copy city 1298 from parent 2, okay, keeping their positional information intact. What does it mean? Counting from left, at the fourth position I have got city 1, fifth position city 2, sixth position city 9, and seventh position city 8. So to get child 1, I am just going to copy these cities 1 to 9, 8 at the fourth, fifth, sixth, and seventh position. All of you, please do that. And if you do that, then you'll be getting a part of the child solution something like this. Can you see 1, 2, 9, 8, and which I have put within the first bracket. You also use first bracket. Okay. So you write down 1, 2, 9, and 8, right within first bracket. City 1 is to be put on fourth position, counting from left. Fifth position, city 2. Sixth position, city 9. Seventh position, city 8. I hope all of you have written. Okay. And close this first bracket. Then you come back. You come back here. So our aim is to find out child 1, and to get child 1, so cities 1, 2, 9, 8 I have already copied from parent 2. Now I'll have to take some information from parent 1 because there will be exchange of properties. Now to get some information from parent 1, what I do, please listen to me. You go to the starting city after the second crossover site lying on parent 1, that is city 8. Let me repeat. You concentrate on the starting city after the second crossover site lying on parent 1, that is city 8. Am I clear to all of you? I am trying to find out the other remaining cities of child 1. And to find that, I am going to concentrate on the first city put after the second crossover site on parent 1, that is city 8. But city 8 has already been taken, so I cannot repeat. The next is city 9. City 9 is also there, so I cannot take it. Then you come back to the starting city of parent 1. Okay, the whole parent 1, that is your city 1. 1 is also taken. I cannot take. Next is city 2. City 2 is also taken already. I cannot take. Next is city 3. 3 is not there. Okay. So now I can select city 3. You see, I have selected city 3 here. You can see I have selected city 3. I hope I am clear to all of you. Okay. Now you go back. So I am here, city 3. Next is city 4. 4 is not yet taken, so you take it. Next is city 5. 5 is not yet taken, so take it. Next is 6. 6 is not yet taken, so take it now. 7. 7 is not yet taken, take it now. Are you getting my point? that completes the cycle. Are you getting my point? Now you'll be getting, so this particular child 1. So 1, 2, 9, 8 we selected first. Then we got 3, 4. Then you come back here, got 5, city 6, city 7. That completes your child 1 tour. Okay. And I have got child 1, and that is a valid child because no city has been taken more than once. You can check it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this is a valid child. Okay. Similarly, you can also find out child 2. How to find out? Very simple. To get child 2, what you do is the cities lying between the two crossover sites on parent 1, that is 4, 5, 6, and 7, you directly copy, and then you concentrate on the first city lying on parent 2 after the second crossover site, that is 7. Then you go to 6. Then you come back to city 3, 4, 5, and so on. You follow this particular procedure and you'll be getting, that is your child 2. All of you, please try. Please try on your notebook and tell me whether you are getting the valid child or not. All of you, please do it. So this is the valid child which you'll be getting. Like 4, 5, 6, and 7 are selected first. Then we go for the city 3, then city 1, then city 2, then city 9, then city 8. This is the principle of the order crossover. And so far as I know, out of all the crossovers used in scheduling genetic algorithm, this is the most popular one. Okay, this order crossover is very frequently used. Okay, I hope I'm clear to all of you. Can I start with the third crossover operator? Let me start. Yes, any doubt? Can I start with the third crossover operator? Let me start. The third one, that is called cycle crossover. That is also very popular. Okay. Now let us try to understand the working principle of this cycle crossover that was proposed in the year 1987 by Oliver et al., Oliver and others. Okay. Now once again, let me take the two parents, parent 1 and parent 2. And once again, I'll request you, you write down on your notebook parent 1 and parent 2. Please note it down, parent 1 and parent 2 on your notebook. Yes, can I start? Now, cycle crossover starts with one starting city selected at random. Okay, and that is denoted by this particular star. So our aim is to determine child 1 and child 2, and to determine child 1 and child 2, we are going to start with a city selected at random as the starting cycle, as the starting city of the cycle. Okay, so let us start with this particular third position as star. Okay, now I'm going to find out child 1. So please write down on your notebook child 1. Now remember, to get child 1, I want to take information from parent 1 first, then I will concentrate on parent 2 according to this cycle crossover. Let me repeat. In order to get child 1, first I will be taking some information from parent 1, and then I will be taking the remaining information from parent 2 in order to get child 1. Okay. Now on the notebook in the third position, you write down city 3. You write down child 1. In the third position, you write down city 3. And once you've written city 3, you find out the possible location of city 3 on parent 2. So this is the location of city 3 on parent 2. That is the first location. Okay. Now at this location, you put the city which is lying on parent 1. That is city 1 is lying at this position on parent 1. Okay. So to get child 1, in the first position, you write down city 1. Let me repeat. Now, city 3 has been selected at the third position. Once you have selected city 3, you find out the location for city 3 on parent 2, and that particular location is the first location. And on that particular location, you put a city corresponding to city 3, okay, lying on parent 1. That is your city 1. So you put city 1 at location 1 to get child 1. So I hope I am clear. And once you've written at the first position city 1, you try to find out the possible location of city 1 on parent 2. You can see the fourth position. Okay. City 1 is occurring at fourth position on parent 2. And its corresponding city on parent 1 is city 4. Are you getting my point? So at the fourth position of child 1, you put city 4. Please do it. At the fourth position of child 1, put city 4. And once you have selected city 4, now you find out the possible location of city 4 on parent 2. That is the second position. So in the second position, you see we have got city 2 on parent 1. So select city 2 in the second position of child 1. I hope you have written city 2 at the second position of child 1. And once you have selected city 2, you try to find out the possible location of city 2 on parent 2. That is this fifth position. And its corresponding city lying on parent 1 is city 5. Okay. So at the fifth position of your child 1, you write down city 5. After you have written city 5, at the fifth position of child 1, you find out the possible location of city 5 on parent 2. This is. And its corresponding city on parent 1 is city 3. That was the starting city of the cycle. Are you getting my point? that completes the cycle. Okay. But after the completion of this particular cycle, still we have got a few remaining position in child 1. Are you getting my point? Now, till now, in order to get child 1, I have taken all the properties from parent 1. So, the remaining properties are to be taken from parent 2. So, directly you copy from parent 2. Are you getting my point? So, in child 1, there is a mixture of properties of parent 1 and parent 2. Okay. And if you do that, then you'll be getting a child like this. So this will be your child 1. Please follow whatever I told. You'll be getting this particular, the child 1. Okay. And if you follow the same principle to get child 2, you'll be getting this as child 2. Please spend some time on practicing this. It will take a little bit time for all of you. See, I'm teaching for so many years. And I can tell so easily, but it is not so easy for you people. And it requires a lot of practice. So please spend some time to find out child 2 and check whether you are getting child 2 or not. Don't get nervous. All the methods I have written it and I'm discussing in details. Okay, and I'm moving very slow to help you people so that all of you can follow me. Okay, and you'll be getting child 2. Okay, is there any doubt here?
I have a doubt.
Please.
Sir, why we have chosen position 3 in parents 1 initially?
You see,
Could be
that, yes, it is selected at random. Okay, so
Yes.
here at random I have selected 3rd position as the starting. You can select any one as the starting position. Out of 9 positions, any one you can select as starting. Accordingly, you will be getting the different children solution. Okay. Same problem, same 2 parents. If you start with another city selected at random, there is a possibility you'll be getting different child solution. Please try. Select 5th as the starting. Try. Select 6th as the starting. Once again you try. Okay.
Okay, sir.
You'll be getting different solution. Okay.
Okay, sir.
I think it is clear.
Yes,
Now,
sir.
now let me start with the next crossover operator, that is called the position based crossover.
Sir, I
Okay.
have a doubt. Excuse me,
Please
sir.
tell me.
Yeah. So this cycle crossover is more like we are determining the crossover site once the cycle ends, isn't it?
Let me please repeat.
Like we are just finding the crossover site, and the position where the cycle ends gives us the crossover site.
See, in cycle crossover, you have to select the starting position of that particular cycle. Okay. And once you have
Yes.
started that particular cycle, you'll have to end it also.
Mm-hmm.
Okay. Now to complete the cycle, to get child
Yes.
1, I'm taking the properties from parent 1
Mm-hmm.
and the remaining properties of child 1 should be taken from parent 2 because
Yeah.
we exchange of properties.
Mm-hmm.
Okay.
My doubt was like we are just finding the crossover site, no? Here
We are
by using a cycle.
no. See, crossover site is selected at random. There are 9 cities, 9 places. Any one can be selected as a crossover site or the starting of the cycle. selected at random, but our aim is to find out two valid children solution from the two parents.
Okay.
Okay,
Okay.
that is the purpose of crossover. Purpose
Yes,
of
yes.
crossover is what? To get the
Uh-huh.
children solution using the properties of the parents by
Mhm.
exchanging the properties of the parents, how to find
Yes.
out the new children solution. Then only the
Because
right
I was just confused with the single point crossover. That's the thing.
single
Because
point crossover you forget for the time waiving.
okay,
It
okay,
is not valid for this type of complicated optimization problem. Are you
okay.
getting my
But
point?
sir, how it
Yes,
is,
yes.
Huh?
sir, but
Use
how it is different?
you use the single point crossover, okay, for the same problem. Use
Mhm.
the single point crossover for the same problem and solve it. There is a possibility you'll be getting invalid child solution. Just try, huh?
Mhm.
Try to one.
Yes.
Okay, you
Okay.
write down. You write down on your notebook. 1
Okay.
second. Parent 1 and parent 2, please write down.
Okay.
All of you, please write down. Parent 1 and parent 2, please write down. All of you. Have you written?
Yes.
Now you take the fifth position.
Mm.
Fifth position means what? So this is the first crossover position, site, second, third, fourth, fifth. That means between 5 and 6, on parent 1, you draw one vertical line.
Yes.
Draw one vertical line.
Yes.
That will be the crossover site for single point crossover.
Mm-hmm.
Are you getting my point?
Yes, yes.
Now, that will be the single point crossover.
Mm.
Okay. Or let me take another example, because sometimes you'll be getting valid children, but you may not get always. You take this as the crossover site. The second one from left between 2 and 3. Please take. Sometimes you may get valid sequence by chance, but you may not get always. Okay.
Yeah.
But I want to get always that valid children. Okay.
I got it. I got it. It was just by chance.
It was by chance. Now you take this particular side between 2 and 3 as a crossover site for single point crossover. And do single point crossover.
Yeah,
All
it
of
is
you say,
invalid. It's
huh?
invalid.
One city is coming twice. There are some missing cities.
Mm.
In the children's solution, one city may come twice,
Mm.
and there could be some missing cities.
Yes.
Okay. To avoid that, we generally go for this type of specialized crossover operators. Okay.
Okay. Mm.
Now you concentrate on this position-based crossover. Now, position-based crossover, that was introduced by Sisworther in the year 1991. Okay. Once again, you write down parent 1 and parent 2. Please write down, all of you, parent 1 and parent 2. Okay. Now to implement the position-based crossover, the principle is very simple. Our aim is to preserve position information of different parent elements in the child solution. So what I do is, we try to locate a few positions denoted by star. So the first one, the fourth one, the seventh one, and the ninth one, these are the fixed position selected. So here I've selected 4 position out of 9. You can also select 3 out of 9 or 5 out of 9. Okay. And this site selection could be at random. Okay. Now, the rule is very simple. Now, the rule is let me read it out. To determine child 1, choose a number of crossover points, say 1st, 4th, 7th and 9th on parent 1, which I've already done. The elements 1, 4, 7 and 9 are directly copied from parent 1 by keeping their position information intact to child 1. Are you getting my point? So what you do is, I'll just show you that child 1, it will become easy for you. See, this is child 1. So 1, 4th, 7th and 9th. Okay, you write down. Other things you keep it blank. City 1, City 4, City 7 and City 9 you write down, keeping their position information intact. And those are taken from parent 1. You can see that. Those are taken from parent 1. 1, 4, 7, 9. Have you written, all of you? If you have written, now these properties are taken from parent 1. So I'll have to take some property from parent 2. So what you do is, you concentrate on the starting position or the starting city of parent 2. What is the starting city of parent 2? Is 3. Okay. Now you concentrate on city 3. Now city 3 has not yet been selected on child 1. Okay. So what you do is, you select city 3 in the second position of child 1. You please write down city 3 in the second position of child 1. Then you concentrate on city 4 lying on parent 2. City 4 has been taken already. Don't take it once again. Then you go to city 5. 5 is not yet taken. So in the third blank position of child 1, you select city 5. Okay. Then you go to city 1 lying on parent 1, but 1 has already been taken. Then you go to city 2. I hope 2 is not yet taken. So you take in the vacant position of child 1. Most probably this is the vacant position. That is the 5th position. Okay. Then you go to city 9, city 8, city 7 and city 6. Follow the same procedure. And if you do it, there is a possibility that you'll be getting your child 1. Okay. So this 1, 4, 7 and 9 we selected first. Then we selected city 3, city 5, city 2, 8, then city 6 also. This is a valid child. You see, no city is coming more than once. Okay. And all the cities have been considered. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you'll be getting the valid child 1. Following the same principle, so to get child 2, what you do is, so this 3, 1, 8 and 6, those are the star position. So directly you copy from parent 2. Then you concentrate on the starting city of parent 1 and go on searching in towards my right. Okay. And if you follow that, then you'll be getting your child 2. All of you please try and check whether you are getting this type of child 2 or not. I hope all of you will be getting this child 2. And once again, you can check its validity this is a valid child. I think I'm clear to all of you how to get child 1 and child 2 using the position based crossover. I hope I'm clear to all of you. Okay. Now I'm just going for another crossover operator which is much more complex to understand. Okay. But
Sir,
you, yes,
sir, for parent 1 and parent 2, we have to take the different crossover site or same?
no, the same star position you consider. Once you have taken the 4 or 3 or 5 star position, you don't change the star position. To get child 1 and child 2, take the same star position. So these are the star positions. You can see that is first, 4th, 7th and 9th are the star position. Okay. Use the same set of 4 star position to get both child 1 and child 2. Don't change it. Okay. Now I'm going for another crossover operator which is called the partially mapped crossover, and in short that is known as PMX. And this PMX, this was proposed by Professor David Goldberg and Lingley in the year 1985. Professor Goldberg, you know, he did most of the foundation work of genetic algorithm. He was a very popular and very popular PhD student of Professor John Holland. Okay. So Professor Goldberg actually did most of the foundation or the fundamental work on genetic algorithm after Professor John Holland. Okay. But this crossover operator has got some failure. I'm just going to indicate that. Let me discuss the principle first. This crossover operator is, I should say, the most difficult to understand. And this particular crossover operator has got some failure cases also. Okay. But let me try to explain. You'll see that it is much more complex compared to all the crossover operators, specialized crossover operators I've used till now. I've discussed till now. The principle, let me try to understand. Once again on your notebook, you write down parent 1 and parent 2 and you draw these two crossover sites selected at random. All of you, please do it. Okay, so I hope all of you have written this. Now let me read it out. Let me also write down on my notebook. Okay, so parent 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then comes parent 2 is 3, 4, 5, 1, 2, 9, 8, 7, 6. Okay. And the crossover sites, let me draw here and let me also draw here. Okay. Now let me read out the rules to be followed in PMX. Select the two crossover sites at random that I've done it. Now our aim is to get child 1 and child 2. let me first concentrate on child 1. The elements 4, 5, 6 and 7 of parent 1. You can see that 4, 5, 6 and 7 of parent 1 lying within two crossover sites, are directly copied to child 1, keeping their position information intact. Okay, so what I do is, so I'm just going to write down 4, 5, 6 and 7. All of you please write down. At the 4th, 5th, 6th and 7th position of child 1, you write down 4, 5, 6 and 7. Okay. So this has to be written fast. Now, to determine the remaining elements of child 1, the search starts with the elements of parent 1 residing in between the two crossover sites. What does it mean? Once again, I'll have to concentrate on the elements of parent 1 residing in between the two crossover sites. So on parent 1, you can see that in between the two crossover sites, we have got cities 4, 5, 6 and 7. Can you locate? Please concentrate on the elements on parent 1 residing in between the two crossover sites. That is your city 4, 5, 6 and 7. Am I clear? Okay. Now, what is the rule? Thus, the second position of child 1 will be filled up by element of parent 2 located at 4th position, that is city 1. Okay. Now, what is the rule? Let me explain the rule first. All of you, please concentrate here. So, to get child 1, 4, 5, 6 and 7 I have already copied in child 1. Once again, you concentrate here. The cities lying on parent 1, lying between the two crossover sites, that is city 4. Am I clear? Find out the possible location of city 4 on parent 2, that is the second position. Now on the second position of child 1, you put 1 because 1 corresponds to city 4. City 1 lying on parent 2 is corresponding to city 4 lying on parent 1. Let me repeat. Concentrate on the first city lying between the two crossover sites on parent 1, that is city 4. Find out the possible location of city 4 on parent 2. That is your second location. 4 is lying on parent 2 at the second location. You mark the second location. And on the second location of child 1, you put city 1 because city 1 lying on parent 2 is corresponding to city 4 lying on parent 1. 4 corresponds to city 1. Then you concentrate on city 5. Find out the location of city 5 on parent 2. This is the location, third location. And city 5 corresponds to city 2. So on the third position, you write down city 2. Then you go for the sixth city. Find out the possible location of city 6, and at this particular location, you write down city 9, which is corresponding to city 6. Then you concentrate on city 7. Find out the location of city 7 on parent 2. At this position, you write down city 8 because 7 corresponds to city 8. Okay. So by doing that, so I hope I'm able to come up to this. Okay. Now the remaining element of child 1 is directly taken from parent 2. That completes your child 1 tour. Okay. And if you do that, then there is a possibility you'll be getting this type of child 1. 3, 1, 2, 4, 5, 6, 7, 8, 9. All of you, please practice. Okay. And following the same procedure, you can also find out child 2. That is nothing but your 4, 5, 3, 1, 2, 9, 8, 7, 6. Please spend some time. If you face any problem, I am there to help you. Okay.
Sir,
But,
sir, in that child one, the 8th position is supposed to be 9, right?
pardon?
In child one, the 8th position, isn't it supposed to be 9? I
Why
would
not?
just
Why 9?
because the 6 corresponding to this one in parent one, and the corresponding side to 6 is 9.
See, 6 corresponds to 9. So this is the position for 6. So here at the end there will be 9. In child 1, last
Okay.
position there will be 9. Okay.
Okay, got
And
it.
at this position 7, this is the location of 7 on parent 2. So you mark the position. 7 corresponds to 8. So 8 should come here. Okay. Now if you have understood, as I told, there are a few failure cases. And I'm just going to show you one such failure case. All of you please write down this special case of parent 1 and parent 2. All of you. On your notebook, you please write down parent 1 and parent 2. And select these two crossover sites at random. Now you carry out PMX to find child 1 and child 2. It's very simple. In child 1, this 3, 4, 5, 6 first you copy to in child 1, first you copy 3, 4, 5 and 6. Then you concentrate here. CT3 is coming here in the first position and 3 corresponds to 5. Although 5 I've already selected, once again 5 is coming here. For the time being, you write down 5 outside also. Next is CT4. This is the possible location of 4. 4 corresponds to 1. So here you write down 1. Then comes your CT5. This is the possible location of 5. Okay. But at this position, I've already taken. So I cannot repeat it. I cannot put 2 here. So don't put. Then you concentrate on 6. This is the location of 6. 6 corresponds to 9. Okay. You can write 9 there. Rest of the thing you take from parent 2, and if you follow that, there is a possibility using PMX, you'll be getting this type of child 1 and child 2. All of you please check. don't lose your patience. It required a lot of practice. I can do it because I did it several times. Okay. It will take little bit time for all of you. And lot of practice is required. Now this is your child 1 and child 2. Now if you concentrate on child 1, it is a failure case because CT5 has been considered twice and CT2 is missing. Okay. So we'll have to make some correction. What type of correction? The CTs which are lying within the first bracket, we cannot disturb. So 3, 4, 5, 6 will remain intact. Okay. And outside CT5, that will be replaced by the missing CT, that is CT2. So it will become 2, 1, 3, 4, 5, 6, 7, 8, 9. And if you do that, so you'll be getting the modified child 1 and modified child 2. Once again, on this particular child 2, CT5 has come twice and 3 is missing. Okay, but we want to disturb anything which are lying inside your first bracket. And outside the first bracket, we have got a 5 here. 5 is replaced by the missing CT, that is CT3. So if you use PMX, you'll have to make this particular the correction. Now remember, these crossover operators are not the unique. You can also design and develop another crossover operator, okay, to solve this type of scheduling problem. For example, we also proposed one crossover operator to solve the scheduling problem. And that particular crossover operator is much more simple. Do you want to listen to that? Okay, you write down. I'm just once again going back to the same example. Okay, in your notebook, you write down. I'm also writing. Take these parents. Okay, so parent 1, I'm also writing, you also write down. This we proposed is very simple. 1, 2, 3, 4, 5, 6, 7, 8, 9. Parent 2 is your 3, 4, 5, 1, 2, 9, 8, 7, 6. And once you've written these two parents, parent 1 and parent 2, you follow the principle of your classical single point crossover, but modify it little bit. Okay. See, according to your classical single point crossover, crossover site can be selected anywhere. So I'm requesting you to select the crossover site between CT4 and 5 lying on parent 1. Draw one vertical line and put star. This is your crossover site. You will not be able to see. This is your crossover site, single point crossover site. Let me repeat. Once you have written parent 1 and parent 2, select the site between CT4 and 5 for the possible single point crossover lying on parent 1. I hope you are able to draw one vertical line with star. That is actually we modified the single point crossover and we added that order information. It's very simple. You need not go for such a complex operator. Now, how to find out child 1 and child 2? Follow the principle of your single point classical crossover operator. Whatever is kept on the left-hand side of the crossover site, that is kept unaltered. Okay. And whatever is lying on the right-hand side, that is swapped, interchanged. Okay. The seat is lying on the bottom will go to the top. So the seat is lying on the bottom of parent 2, that is 29876. You directly copy on child 1, 29876. Have you copied? Have you written 29876 after the crossover site of child 1? Whatever is lying on parent 2, that will go to the top, and whatever is lying on parent 1, that will come down. Okay. And once you've got this 29876, all such information I have taken from parent 2. Now I'll have to take some information from parent 1. What we do, we come back to the starting position of parent 1. That is CT1. Okay. Now CT1 is not yet taken. So on the starting position of child 1, you take CT1. Next is CT2. 2 has already been taken. Don't take it once again. Then CT3. 3 is not yet taken. So take 3 here. Then comes 4. 4 is also not taken. So take 4 here. Then comes 5. 5 is also not taken. Take 5 here. Then comes 6. 6 has already been taken. 7 has already been taken. In fact, I have completed child 1. Now you check child 1. 1, 3, 4, 5, 2, 9, 8, 7, 6. Follow the same principle to get your child 2. And you see, a particular city has been considered only once, and there is no failure cases. It is so simple. This was our proposal, and it is competition. It was very fast compared to your complicated PMX, and moreover, there is no failure case here. I hope all of you got our proposal. It was very simple. Okay. Now, after discussing these 5 crossover operators, specialized crossover operator, and our proposal, that is the 6th one, which one is the best? What is your opinion? Huh? Out of these 6,
last one.
Last one.
Yes.
Now, even the last one was not the best. Are you getting my point? We tested on a number of problems. Okay, and ultimately I had to conclude that the performances of these specialized crossover operators are problem dependent, function dependent. That was actually our concluding remarks. Although our proposal was computationally very fast, might be the fastest, okay, but no crossover operator could be declared as the best, okay, and their performances are found to be problem dependent. So I hope I am clear to all of you. Okay, so now onwards, being one of my students, please do not make this particular mistake of using the conventional crossover operator to solve the scheduling problem. Please do not make this mistake. I have seen many people making this mistake. But please, being one of my students, do not commit this mistake. Okay, then only my all effort will be justified. Otherwise, all my effort and all my trial, it will have no value at the end. Okay, so don't follow the conventional crossover operator, even if you are advised to use, do not use. Then also I am requesting you, because you are going to make mistake. Don't make this particular mistake. Might be in your PhD work, you'll have to use some optimization related to scheduling problem. Some of you might be using. So my suggestion is, do not use the conventional crossover operator. Okay. So
The
with this,
switch method can be used with double crossover site.
double crossover site can be designed also, no problem. You can do it. You are right. Okay. 2-point crossover can be designed following the similar procedure. It is possible. Okay. So do you have any other doubt, or shall I stop today? Let me stop here today. Please.
No, sir. Yes. Yes, sir. I had a query in the partially connected system. Like, I wanted to know why it was difficult. Since in case of a partially connected system, the path will be more defined. Like, the number of possibilities will be less, right? And I guess computation time will be.
You see, PMX. Are you talking about PMX? Are you talking about PMX or which one?
The partially connected cities, sir. The maps.
Partially mapped crossover. Are you talking about that?
No, sir. The symmetric. Sir, the symmetric and the asymmetric cities.
You see, for asymmetric cities and partially connected TSP, it is more difficult to solve because connectivity between the two cities may not be available always. Supposing that your genetic algorithm is going to give one optimal solution, but that particular direct connectivity may not be available. The road may not be available between the two cities in both the ways. Are you getting my point? Generally, it is available in both the ways, but it may not be always true. That is why. Okay?
Yes, sir. Yes, sir. Actually, I didn't think it from the solution point of view. Yes, sir.
Okay.
Thank you, sir. Yes.
Now, I'm just going to stop today. Now, the next class will be on Wednesday, that is 11th. But you know, on 11th, I'll have to take the test for the soft computing. So I'll be starting the test on 11th at 12 p.m. So I'll start the exam, then I'll be taking your class. Okay. So might be in place of 12, I may start 5-10 minutes after 12. Might be we are going to start 10 minutes after 12. Okay. So on Wednesday, that is 11th November, in place of 12 p.m., I'm going to start taking your class at 10 minutes past 12. That is 12:10 p.m. Please note it down. Okay. Okay. So let me stop here today.